Imagine a universe where the past, present, and future are not fixed but fluid, where every decision you make could ripple across time itself. What if everything you thought you knew about cause and effect was just one thread in a much larger cosmic tapestry? The very fabric of reality might be far more mysterious and interconnected than we ever dared to dream. Time travel isn't just a science fiction trope. It's a profound scientific and philosophical puzzle that has captivated the greatest minds for centuries, challenging our understanding of existence itself. We begin with a powerful insight from physicist John Wheeler, who once said that time is what prevents everything from happening at once. That single idea opens the door to a realm of breathtaking possibilities. In this video, we're going to explore 20 of the most mind-bending theories on time travel and cosmic paradoxes, concepts that stretch the limits of imagination, from the famous grandfather paradox to the mysterious bootstrap effect. These aren't just abstract ideas, they represent the cutting edge of theoretical physics and cosmology, inviting us to rethink reality in ways that are both thrilling and deeply humbling. Why does this matter? Because these theories do more than fuel our curiosity. They push the boundaries of human knowledge, blurring the lines between science and philosophy, between what is possible and what is permissible within the laws of the universe. By the end of our journey, you won't just see time as a straight line moving from past to future. You'll see it as a rich, dynamic tapestry of possibilities, where every moment is connected in ways we are only beginning to understand. So get ready to question everything you thought you knew about time and space, and join us as we embark on an extraordinary exploration of the cosmos' greatest mysteries. Picture this: you've built a time machine, stepped into the past, and with one unintentional action, you prevent your own grandparents from ever meeting. If that union never happens, then your parent is never born, and by extension, neither are you. So how could you have possibly traveled back to set these events in motion? This is the grandfather paradox, the most famous and troubling logical puzzle at the heart of time travel. It's a concept that immediately exposes the profound inconsistencies that arise if we assume the past can be altered. For decades, this thought experiment has been a central battleground for physicists and philosophers, forcing them to confront a critical question: is history a fixed, unchangeable record, or is it something more fluid, capable of branching into new realities? One compelling resolution comes from the idea of alternate timelines or parallel universes. In this view, your journey to the past doesn't rewrite your own history, but instead forks off an entirely new reality, a separate timeline where you were never born, while your original timeline remains untouched and you continue to exist within it. This multiverse approach elegantly sidesteps the paradox by suggesting that every possible outcome plays out somewhere, preserving the logical chain of cause and effect in each individual universe. It's a popular solution in science fiction for good reason, as it allows for the drama of changing the past without the logical nightmare of erasing yourself from existence. Another fascinating proposal is the concept of self-consistency, where the universe itself might enforce a kind of cosmic censorship. The idea here is that the laws of physics would simply prevent any action that creates a paradox from ever occurring. You might intend to interfere with your grandparents' meeting, but some unforeseen event, a sudden distraction, a slip of the hand, an unlikely coincidence, would always intervene to stop you. Your free will to change the past would be subtly overruled by the universe's need to maintain a consistent and paradox-free timeline. In this model, the past is immutable. Your travel back in time was always a part of history, and your actions there can only ever fulfill what has already happened. This paradox is far more than just a fun plot device for movies and books. It strikes at the very core of our understanding of causality, identity, and reality itself. If time travel to the past were possible, would we have any real agency, or would we merely be playing out a predetermined role in a story that's already been written? The grandfather paradox doesn't offer easy answers, but it provides a powerful framework for exploring the deepest rules that might govern time and our place within its flow. Now consider an even more bewildering possibility. What if an object, an idea, or even an entire person has no origin at all? Imagine traveling to Elizabethan England and handing William Shakespeare a complete set of his own future plays. He then publishes them, they become celebrated works, and centuries later you discover them, memorize them, and travel back to deliver them to him once again. The plays exist, but they were never actually created by anyone. They are caught in an infinite loop with no beginning and no end. This is the Bootstrap paradox, a concept that completely unravels our traditional understanding of cause and effect. Unlike the grandfather paradox, which creates a logical contradiction, the Bootstrap paradox presents a different kind of problem. Something is brought into existence without any point of origin. It's a closed causal loop where the effect becomes its own cause. The information or object is literally bootstrapped into reality, hence the name. There's no creator, no initial spark, just an endless cycle where the thing has always existed within that loop. This isn't just a wild thought experiment. Certain solutions within Einstein's theory of general relativity, known as closed time-like curves, mathematically allow for such loops to occur. In these regions of spacetime, the path of an object could curve back on itself, meeting its own past. We see this depicted powerfully in stories like Robert Heinlein's All You Zombies or the film Interstellar, where the protagonist Cooper finds himself inside a tesseract, able to interact with his daughter's past. He desperately sends the data that will save humanity, but the critical question remains: who originally discovered that data? The answer is no one. The information was never invented. It was always just passed back through time, a gift from the future with no author. This paradox forces us to confront the very nature of existence and creation. If something can be self-created, what does that say about our own reality? Are there ideas, inventions, or even historical events that might be caught in such a loop, appearing to have an origin but truly being timeless? The implications for free will are perhaps even more unsettling than those of the grandfather paradox. If the future can influence the past in a consistent loop, then our actions in the present might not be the result of our own choices, but rather the inevitable fulfillment of a timeline that is already complete. Your decision to, say, become a scientist might feel like your own, but what if that decision was subtly influenced by a future version of yourself who traveled back to ensure it happened? This introduces a form of determinism where every event is predestined, locked into a loop that has simply always been. It challenges the very core of human agency, suggesting that our sense of control over our lives might be an illusion woven into the fabric of a pre-existing cosmic story. But what if the universe itself provides an escape from these mind-bending paradoxes? In 1957, a brilliant young physicist named Hugh Everett proposed a radical solution that forever changed our conception of reality. He suggested that at every moment where a quantum event has multiple possible outcomes, the universe doesn't just choose one. It branches into entirely new versions of itself, each one realizing a different possibility. This is the many worlds interpretation, and it transforms time travel from a dangerous rewriting of history into an incredible journey across the infinite landscapes of the multiverse. Imagine stepping into your time machine with the intention of altering a single event in your past. According to Everett's vision, you wouldn't be rewriting your own history. Instead, the moment you arrive in the past and take any action, you cause a new branch in the timeline to split off from the original. In this newly created universe, your actions have consequences perhaps your grandparents never meet and you are never born. But that's not your universe. You came from the original branch where your grandparents did meet and you were born, and that timeline remains completely untouched and unchanged. You haven't erased yourself. You've simply hopped over to a new, parallel reality where the rules of cause and effect remain perfectly consistent because your own personal history is anchored in the universe you left behind. This provides an elegant and powerful solution to the grandfather paradox and other logical nightmares of time travel. There's no cosmic censorship needed to stop you, and no need for the universe to enforce frustrating consistency. You are free to act, and the multiverse simply expands to accommodate every possible choice, every chance occurrence, creating a sprawling tapestry of realities where everything that can happen does happen somewhere. Your identity isn't lost in the process. It's just that your story becomes one thread in an infinitely larger narrative. The you in this new branch is a version that has always existed here, with a slightly different history that now includes your arrival. Yet this breathtaking idea comes with its own profound philosophical implications. If every quantum decision spawns a new world, then there are an infinite number of universes, each with countless variations of you, living out every possible life. There's a version of you who became an astronaut, another who never left their hometown, and another who made a different choice at a critical moment this very morning. This raises deep questions about what identity even means. If there are infinite versions of you, in what sense are you a unique individual, and what about continuity? The you that steps out of the time machine in a new universe may feel like the same person, but you are now forever separated from the timeline of your origin, a traveler who can never truly go home because home is a branch on the tree of reality that you have now left behind. This interpretation doesn't just solve time travel paradoxes. It invites us to see ourselves and our choices as part of a vast, dynamic, and endlessly creative cosmic process. Now let's venture into the bizarre and beautiful world of quantum mechanics, where the rules of reality seem to play by an entirely different playbook. Here we encounter a phenomenon so strange that even Einstein famously called it spooky action at a distance. This is quantum entanglement, a profound connection that can instantly link two particles across vast cosmic distances. But what if this mysterious link could do more than just connect points in space? What if it could also bridge different points in time? This brings us to a theory that suggests entanglement might be the key to a form of quantum time travel, allowing information to flow backwards through time and challenging our most fundamental ideas about cause and effect. In a standard entanglement experiment, two particles are created together, becoming linked in such a way that measuring the property of one, like its spin or polarization, instantly determines the property of the other, no matter how far apart they are. This connection seems to defy the universal speed limit of light, operating instead on a principle of immediate correlation. Now, some theoretical physicists are asking an even more radical question. Could particles become entangled not just across space, but across time itself? Imagine a particle that is entangled with its own past or future version. In such a scenario, measuring the particle today could instantly influence what its state was yesterday or what it will be tomorrow. This isn't about building a machine to physically send a person back in time. It's about the potential for information itself to travel along these quantum threads into the past or future. This idea moves from pure speculation into the realm of tantalizing possibility, thanks to experiments in quantum teleportation. Scientists have already successfully teleported the quantum state of a particle from one location to another using entanglement. While this doesn't involve moving matter through space, it does involve the instantaneous transfer of information. If we can teleport information across space, could we devise a way to teleport it across time? The mathematics suggests it might be possible to create a quantum circuit where a measurement made on a particle now effectively sends a signal backwards, influencing an event that has already occurred. This wouldn't allow you to go back and meet your grandfather, but it might allow a single bit of data to be received before it was ever sent. The implications of this are staggering. It challenges the very notion that time is a strict one-way flow from cause to effect. At the quantum level, time might be far more flexible and interconnected than we ever imagined. If information can indeed be sent to the past, it opens up the possibility of closed time-like curves on a microscopic scale, tiny loops in time where data can circle back on itself. This blurs the line between time travel and communication, suggesting that future technologies might one day allow us to receive messages from the future or send warnings to the past. Of course, this remains highly theoretical, buried under layers of complex math and formidable practical obstacles, not least of which is the potential for paradox. But the mere fact that it is being seriously considered by physicists shows just how deeply our understanding of time is being rewritten by the quantum revolution. Now let's shift our gaze from the quantum realm to the grandest structures in the cosmos, where the fabric of space-time itself might be twisted into the ultimate time machine. Imagine threads of pure energy left over from the very birth of the universe, thinner than a proton yet so dense that a single inch might weigh more than a mountain. These are cosmic strings, hypothetical cracks in the universe's structure, theorized to have formed during the intense phase transitions just after the Big Bang, when the fundamental forces of nature were settling into place. While they've never been directly observed, their potential existence opens up a breathtaking possibility for time travel that relies not on futuristic technology, but on the raw, ancient architecture of the cosmos itself. The brilliant physicist Richard Gott III explored this idea in depth, proposing an ingenious mechanism. He suggested that if two of these unimaginably dense cosmic strings were to fly past one another at a significant fraction of the speed of light, their immense gravitational fields would warp the spacetime around them in an extraordinary way. Picture two incredibly taut, ultra-heavy strings moving in parallel but opposite directions. The gravity they produce wouldn't just create a well in space-time. Under the right conditions, it could twist it into a closed loop, a path known as a closed time-like curve. If you were to pilot a spaceship on a precise figure-8 course around these passing strings, you could find yourself returning to your starting point, not just in space, but in time. You would have completed a journey that brings you back to the moment you left, effectively traveling into your own past. What makes this theory so compelling to physicists is that, unlike many other time machine blueprints, Gott's cosmic string solution doesn't require any exotic matter with negative energy density, a substance that may not even exist. It operates purely within the known bounds of general relativity, using gravity alone to perform its time-bending trick. This gives it a veneer of plausibility that other models lack, as it relies on the proven warping effects of mass and energy on the spacetime continuum. In a way, it turns the universe's own leftover relics into a natural time machine, a feature perhaps built into the cosmos waiting for a sufficiently advanced civilization to find and use it. Of course, the practical challenges are, to put it mildly, astronomical. First, we have no confirmed evidence that cosmic strings actually exist. though some cosmologists believe the subtle patterns in the cosmic microwave background radiation might one day reveal their telltale signatures. Second, even if we found them, the energy needed to maneuver them into the required high-speed configuration is far beyond anything we can conceive of harnessing. We're talking about moving objects with the mass of entire stars at nearly the speed of light. And finally, the precision required for the figure 8 flight path is unimaginable. A tiny error could mean missing the time loop entirely, or worse, being torn apart by the incredible gravitational tides near the strings. Yet, the sheer elegance of the idea captures our imagination. It suggests that time travel might not be something we invent in a lab, but something we discover out in the universe, a natural phenomenon woven into the very fabric of reality, much like black holes or gravitational waves once were before we confirmed them. If such strings are real, they could be the ultimate hidden highways of time, lurking in the vast emptiness between galaxies, offering a way to navigate the fourth dimension using the universe's own primordial scars. But what if the most extreme time machine in the universe isn't something we could ever build, but is instead a natural feature of the cosmos lurking in the darkness? To understand this, we must venture to the edge of a black hole, where the very laws of physics are stretched to their breaking point. According to Einstein's general theory of relativity, gravity isn't just a force that pulls on objects, it's a curvature of space-time itself. The more massive an object, the deeper the curvature, and the more it warps the fabric of time around it. Nothing in our universe warps space-time more profoundly than a black hole, an object so dense that not even light can escape its gravitational grasp. And it's here, in this region of extreme gravity, that time itself begins to behave in astonishing ways. This phenomenon is called gravitational time dilation. Imagine two identical clocks, one placed in a powerful gravitational field, like near a black hole, and the other far away in the emptiness of space. The clock near the black hole will tick noticeably slower. It's not a mechanical error. Time itself is literally passing at a different rate. Now, scale that thought experiment up to a human journey. If you were to pilot a spacecraft on a mission to orbit a black hole, getting perilously close without crossing the point of no return, the event horizon, and then return to Earth, you would have experienced something truly mind-bending. For you, the journey might have felt like a matter of hours or days, but back on Earth, decades, centuries, or even millennia could have passed. You haven't traveled to the past, but you have effectively leaped far into the future relative to everyone you ever knew. This is the only form of time travel that is not only theoretically sound but actively proven and accounted for in our modern technology. The Global Positioning System, or GPS, provides a perfect, everyday example. The satellites in the GPS network are orbiting high above Earth, where our planet's gravitational pull is slightly weaker. Because of this, time actually runs faster for the satellites by a tiny fraction of a second each day compared to clocks on the ground. If the engineers didn't constantly correct for this relativistic effect, the entire system would become useless and your navigation app would lead you astray within minutes. This proves that time dilation is not science fiction. It's a fundamental part of how our universe operates. A black hole simply takes this same principle and amplifies it to an incredible extreme, turning a subtle effect into a powerful engine for time travel into the future. This concept was masterfully and heartbreakingly depicted in the film Interstellar, where the crew visits a planet orbiting the supermassive black hole Gargantua. Every hour they spend on that world's surface, with the black hole's immense gravity slowing their time, equates to 7 years passing for their colleague waiting on the ship and for everyone back on Earth. The emotional weight of that scenario is staggering. They are losing the people they love with every minute they spend trying to solve a crisis. It's a dramatic illustration, but it's grounded in real physics. The closer you get to the event horizon, that ultimate boundary of a black hole, the more extreme the time dilation becomes. At the very edge, from an outside perspective, time would appear to stop completely, freezing you in a single moment for all eternity. This naturally leads to a tantalizing question. If we can use a black hole's gravity to travel to the future, could we also use it to travel to the past? Some theories, particularly those involving a specific type of black hole known as a rotating or Kerr black hole, suggest the answer might be yes. The mathematics describing a rotating black hole reveals a much more complex interior structure than a simple point of infinite density. The equations suggest the possibility of a ring-shaped singularity and the potential existence of a wormhole, a tunnel through space-time at its center, which could theoretically connect to another point in time or space. This isn't a guaranteed feature of all black holes, and the stability of such a passage is highly questionable, often requiring exotic matter to hold it open. But the mere mathematical possibility bridges our understanding from using black holes as natural time dilation engines to considering them as potential gateways, a concept that seamlessly connects to our next incredible theory. But what if the most promising path to the past doesn't require navigating the terrifying edge of a black hole, but instead involves finding a cosmic shortcut? Imagine a tunnel bored right through the fabric of spacetime itself, connecting two distant points in an instant. This isn't just a science fiction fantasy. It's a serious theoretical concept born from Einstein's equations of general relativity, known as a wormhole or an Einstein-Rosen bridge. Initially conceived as a mathematical curiosity, these hypothetical structures could be far more than just shortcuts across space. They might very well be the blueprint for the universe's most incredible time machine. Think of spacetime not as a flat sheet, but as a vast, multidimensional landscape with folds and wrinkles. A wormhole would be like a tunnel that punches straight through the fold, connecting two separate points that would otherwise be incredibly far apart. If you could create or find a stable wormhole, you could step into one end in your backyard and emerge moments later near the star Alpha Centauri, or even in a completely different galaxy. The sheer potential for interstellar travel is staggering, but the implications for time travel are even more profound. The entrance and exit of a wormhole aren't just linked in space, they are also two distinct moments in the timeline of the universe. This means that walking through could transport you not just across the cosmos, but across centuries. How could a tunnel in space become a gateway to another time? The secret lies in a concept we've already explored: time dilation. According to relativity, time passes at different rates depending on gravity and velocity. So, to transform a wormhole into a time machine, you would need to create a significant time difference between its two mouths. One ingenious method, proposed by renowned physicist Kip Thorne and his colleagues, involves taking one end of the wormhole and moving it at a velocity close to the speed of light. Because of time dilation, that end would age much more slowly than the stationary end left on Earth. Another method would be to place one mouth near an intense gravitational field, like a neutron star where time crawls. After a while, you would have two connected points in space that exist in different times. If the moving mouth experienced only 10 years while the stationary one experienced 100, then stepping into the stationary end would send you 90 years into the past relative to when you left. You'd be walking into history. The real challenge, and the reason we don't have wormhole time machines today, is stability. The equations of general relativity allow for wormholes, but they also predict that these tunnels would be incredibly unstable, collapsing into a black hole the instant anything, even a single photon of light, tried to pass through. The only theorized way to hold them open is with a substance known as exotic matter. This isn't just unusual matter. It's a hypothetical material that possesses negative energy density or negative pressure, effectively having anti-gravitational properties that could prop the wormhole's throat open. While tiny amounts of negative energy have been demonstrated in lab experiments like the Casimir effect, the colossal quantities needed to stabilize a traversable wormhole are far, far beyond our current capabilities, and it's entirely possible that such matter cannot exist in the required form. Yet, the work of visionaries like Thorne has moved wormholes from pure mathematical abstraction into the realm of what might be physically possible, even if it remains forever out of practical reach. They represent a tantalizing possibility that the universe's own rulebook might contain the instructions for time travel, waiting for a civilization advanced enough to understand and manipulate the deepest layers of reality. If they do exist, either as natural features of the cosmos or as artifacts of a supremely advanced technology, the secrets they might hold are beyond imagination. Could they be used for observation, allowing us to witness historical events without interference? Or would they inevitably create paradoxes that threaten the fabric of causality itself? The existence of a stable wormhole would force us to confront these questions not as fiction, but as a fundamental part of our universe's operating system. But what if the universe has a built-in safety feature, a set of cosmic rules that ensures time travel never creates a paradox in the first place? This brings us to a profoundly elegant idea proposed by the Russian astrophysicist Igor Novikov. Known as the self-consistency principle, it offers a simple yet staggering solution. You cannot change the past because any attempt to do so would have already been a part of that past. In this view, history is a single, immutable tapestry. Your journey back in time was always an event that occurred, and your actions there can only ever complete the loop of what has already transpired. There is no rewriting, no branching, no altering, only the fulfillment of a story that has already been written with your time travel adventure included. This principle completely sidesteps the terrifying logical nightmares of the grandfather paradox by making them impossible. Imagine you travel back with the noble intention of preventing a tragic accident that took a loved one's life. You arrive on the scene full of hope and determination, only to find that your very presence causes a distraction, or you accidentally knock over a crucial object, or your warning is misunderstood. And in a cruel twist of fate, it is your intervention itself that directly causes the very accident you came to stop. Your action didn't change the past, it was always the cause. The event and your attempt to prevent it were locked together in an inescapable, self-consistent loop from the beginning. The universe, in this model, operates with a kind of perfect narrative consistency, where cause and effect are preserved at all costs, even if it means our intentions are constantly being co-opted to serve a predetermined history. For many physicists, this is a deeply comforting idea. It preserves the sacred rule of causality that cause must always precede effect, and it does so without requiring an infinite number of branching universes or undiscovered physical phenomena. The laws of physics remain clean and paradox-free. The mathematics of general relativity that allow for closed time-like curves are perfectly compatible with Novikov's principle. These curves simply force events to be consistent, not contradictory. It suggests that if time travel is ever possible, it will operate under these strict, non-negotiable constraints. You would have the illusion of free will during your journey, but every choice you make would inevitably lead you to play your exact, preordained part in the historical record. However, this elegant solution comes with immense philosophical baggage. If our future actions are already set in the stone of the past, then what does that say about our free will? Are we truly making choices, or are we merely actors reading lines from a script written by the universe itself? The Novikov principle leans heavily toward a deterministic view of reality, where the entire timeline is fixed from start to finish. Your feeling of making a decision is just that, a feeling. The outcome was determined long ago, perhaps even at the birth of the universe. This can feel deeply unsettling, as it challenges our fundamental sense of agency and purpose. It raises the haunting question: if we cannot change the past or truly choose a different future, is the concept of time travel even meaningful? Or is it just a guided tour through a museum where all the exhibits are already behind glass? This theory doesn't just resolve paradoxes, it forces us to confront the very nature of destiny and our role within a cosmos that might be far more predetermined than we are comfortable admitting. This leads us to a theory that is both mathematically elegant and philosophically jarring, a concept that asks us to let go of everything we feel about the passage of time. What if the distinction between past, present, and future is nothing more than a persistent and powerful illusion crafted by our own consciousness? This is the heart of the block universe theory, a model where time is not a river flowing from a source to a sea, but a vast, static, four-dimensional landscape where every event that has ever happened or ever will happen simply is. In this breathtaking view, the entire history and future of the cosmos is frozen together into a single, unchanging structure, a block, where time is just another coordinate, much like length, width, and height. The block universe isn't a fringe idea. It falls naturally out of Einstein's own equations of general relativity. In the mathematics that describe our reality, the variable t for time is treated no differently than the variables for spatial dimensions. There is no special now point in these equations. They simply describe a universe where all events are equally real and existent. From this perspective, your birth, your reading of this sentence, and every moment of your future are all fixed points in this grand cosmic block, just as real and permanent as the city of Paris is a fixed point on the map of Earth. You don't move through time in this model. Your consciousness simply illuminates different, successive slices of the block, creating the subjective feeling of a present moment that is always advancing. This has a profound implication for time travel. It ceases to be a matter of dangerous alteration and becomes a simple matter of navigation. If you could somehow step outside of your sequential experience and move through the time dimension as easily as we walk through space, visiting the year 1920 would be no more paradoxical than visiting another country. You wouldn't be changing history, you'd simply be accessing a different region of the static, four-dimensional reality. The past isn't gone and the future isn't unborn. They are just other places in the block, permanently existing. This makes the concept of paradox almost meaningless, as every event is already set in its proper relation to every other event. Yet, this elegant solution forces us to confront one of the most difficult questions in all of science and philosophy. If the future is already out there, complete and waiting, then what becomes of free will? Our every decision, our every thought, feels like a genuine choice that shapes an open future. But the block universe suggests that those choices were determined long ago, baked into the structure of reality. We are like readers immersed in a book, feeling suspense about what happens next, even though every word on every page is already printed. This determinism can feel deeply unsettling, as it challenges our very sense of agency and purpose. So why then do we have such a powerful and universal experience of time passing? Why does it feel like a flowing river rather than a frozen glacier? Some physicists and philosophers point to the second law of thermodynamics, the inevitable increase of entropy, or disorder, in the universe. Our brains might be wired to perceive this relentless march toward disorder as the arrow of time. creating a psychological arrow that points from low entropy, the past, to high entropy, the future. Others suggest it is a fundamental property of consciousness itself, that our awareness creates the illusion of a moving now as it scans across the block, much like a spotlight moving across a stage illuminates one actor at a time, even though all the actors are standing there together in the dark. The block universe theory offers a stunningly simple and paradox-free framework for understanding time travel, but it raises as many questions as it answers, particularly when we try to reconcile it with the bizarre, probabilistic world of quantum mechanics. If the entire universe is a single, fixed block, how do we account for the fundamental uncertainty of quantum events, where particles exist in a haze of probability until they are observed? This apparent conflict between the deterministic block and the indeterminate quantum realm is one of the greatest puzzles in modern physics, a tension that drives us toward even more radical theories that attempt to weave these two visions of reality into a single, coherent tapestry. Now let's dive into one of the most baffling and counterintuitive ideas in all of physics, a concept that seems to turn cause and effect completely upside down. We're moving from the grand, fixed block of the universe to the fuzzy, probabilistic world of quantum mechanics, where the rules of reality are anything but straightforward. Here, at the smallest scales of existence, we find evidence that the future might not just be influenced by the past, but might actually reach back and influence it. This is the theory of quantum retrocausality, and it suggests that time's arrow might be a two-way street in the quantum realm. The most famous, and perhaps most mind-bending, demonstration of this comes from a class of experiments known as delayed choice quantum erasers. Imagine a simple setup where a single particle of light, a photon, is fired toward a screen with two slits. As it passes through, it behaves like a wave, creating an interference pattern on a detector behind the screen, a signature that it passed through both slits simultaneously. This is the famous double-slit experiment, weird enough on its own, but the delayed choice version adds a spectacular twist. Scientists can wait until after the photon has already passed through the slits and is traveling toward the detector before they decide how to measure it. They can choose to measure which slit it went through, which forces it to act like a particle and wipes out the interference pattern. Astonishingly, this late decision seems to retroactively change the photon's behavior back in time at the slits. It's as if the photon's past is not fixed until a future measurement defines it. This isn't some flawed interpretation or a trick of perception. The mathematics of quantum mechanics, which has been proven accurate time and again, allows for, and some argue, even implies that correlations can flow backwards in time. In these experiments, the choice made in the present appears to solidify what happened in the past. The particle's history remains in a blurred, undefined state of probability until the moment it is observed. This doesn't mean we can send a message to the past or prevent a historical event. The effect is subtle, statistical, and confined to the quantum world. It doesn't allow for a human to go back and meet their younger self, but it does violently challenge our classical, intuitive notion that the past is a single, immutable record. Instead, it paints a picture where the past and future are in a constant, intimate dialogue, with the present acting as the moment where potentialities collapse into a single, consistent reality. The implications of this are enough to make your head spin. It forces us to ask, are our actions in the present truly creating the future, or are they just fulfilling a story that the future has already written? If a particle's path can be influenced by a measurement yet to come, could our own choices, on some imperceptible level, be subtly nudged by the needs of a future that already exists? This isn't to say our lives are predestined in a fatalistic way, but it does introduce a radical form of interconnectedness where time might not be the linear progression we feel it to be. Our sense of a one-way flow from cause to effect could be a macroscopic illusion, an emergent property that only appears when we zoom out from the quantum weirdness to the world of everyday objects. Naturally, this opens up profound philosophical doors about the nature of reality itself. If the future can influence the past, then the entire timeline might be a self-consistent, self-correcting whole, much like the Novikov self-consistency principle we discussed earlier, but now operating at the most fundamental level of reality. The universe, in this view, ensures that all events past, present, and future are in harmony with each other, even if that means allowing information to flow backwards to make everything fit together neatly. This could be the underlying mechanism that prevents paradoxes from ever occurring, a fundamental law of cosmic consistency woven into the fabric of quantum mechanics. While scaling this effect up to the human scale remains firmly in the realm of speculation, its mere existence at the quantum level is a powerful reminder that the universe is far stranger and more wonderfully interconnected than our everyday experiences could ever suggest. Now we arrive at a theory that takes us from the concrete equations of physics to the deeply personal realm of the mind. What if time isn't a fundamental property of the universe at all, but rather a construct of our own consciousness? This idea suggests that without a mind to observe it, to string events together into a narrative, time might not exist in any meaningful way. It's a concept that lives at the fascinating intersection of theoretical physics, philosophy, and cognitive science, proposing that the flow of time is not something we discover out in the world, but something we actively create within our own heads. This notion finds a curious echo in the strange world of quantum mechanics, particularly in the famous thought experiment of Schrödinger's cat. In that scenario, a cat in a box is simultaneously alive and dead until an observer opens the box and looks inside, at which point the possibilities collapse into a single reality. The act of observation itself seems to play a crucial role in determining the outcome. Some interpretations extend this idea to time itself, wondering if the past, present, and future remain in a fluid, undefined state until a conscious mind observes and solidifies them into a linear sequence. In this view, time travel might not require a physical machine warping space-time, but could instead be achieved through a profound alteration of one's own perception or state of consciousness. This is a theme that has captivated science fiction for decades. Films like Arrival explore this beautifully, where learning an alien language rewires the protagonist's brain to perceive time not as a linear path but as a complete whole, allowing her to experience memories of the future as vividly as memories of the past. It suggests that if we could truly unlock the full potential of our minds, we might be able to step outside our default perception of time's arrow and experience reality in a completely different way. This isn't about building an engine, it's about achieving a state of enlightenment or tapping into a deeper layer of awareness that is usually hidden from us. While this theory is not part of mainstream physics and veers into the speculative realms of metaphysics, it serves a powerful purpose. It forces us to confront the uncomfortable truth that everything we know about the universe, including the steady tick of time, is filtered through the lens of our own perception. Our brains are not passive recorders of reality. They are active interpreters, taking in a chaotic storm of sensory data and assembling it into a coherent, linear story that we call our lives. This psychological arrow of time, our compelling feeling that the past is fixed, the present is happening, and the future is unknown, may be the most real time we ever know, regardless of what the equations say. This perspective doesn't provide blueprints for a time machine, but it offers a profound shift in how we think about our place in the cosmos. It encourages a deep humility, reminding us that the laws of physics as we understand them are descriptions of a reality perceived by human mind. If consciousness does play a role in shaping time, then the journey through it becomes intimately personal, a voyage of inner space as much as outer space. It connects the vast cosmos to the individual experience, suggesting that the greatest mystery of time might not be light years away, but is happening right here inside each and every one of us. But what if the most formidable obstacle to time travel isn't a complex equation or an exotic material, but a fundamental, unwavering law of the universe itself? This brings us to a concept that underpins our entire experience of reality, the arrow of time. Unlike the spatial dimensions where we can move freely back and forth, time has a stubborn, one-way direction. We remember the past, we anticipate the future, and we can never reverse the flow. The reason for this, according to the second law of thermodynamics, is entropy. Entropy is a measure of disorder, and this law states that the total entropy of a closed system, like our universe, can only increase over time. It's the reason ice melts in your drink, why a dropped glass shatters, and why you can't unburn a log. The universe is on an irreversible journey from a state of order to a state of maximum disorder. This relentless increase in entropy is what gives time its arrow. Think of the past as a state of lower entropy, more ordered, more structured. This is why we can remember it. There's a clear sequence of events, like pages neatly arranged in a book. The future, by contrast, is a state of higher entropy, more disordered, more random. We can't remember it because it hasn't happened yet. The pages are blank and scattered. To travel back in time would mean moving from a high entropy state to a low entropy state, effectively forcing the universe to unmix your coffee, unshatter the glass, and unscramble an egg. On a cosmic scale, this appears utterly impossible. It would be like trying to force a river to flow uphill against the combined weight of every drop of water that has ever flowed down it. This presents the ultimate physical barrier for any would-be time traveler. Your machine might perfectly warp space-time, but if it can't also locally reverse the arrow of entropy, your journey to the past would be a surreal and catastrophic failure. Imagine arriving in ancient Rome only to find that the very atoms of your body and your ship are still obeying the future's tendency toward disorder. You might instantly decay, your molecules scattering into a more probable, disordered state relative to that low entropy past. You wouldn't just be an anachronism, you'd be a thermodynamic paradox, a bubble of future chaos erupting into an ordered past, and the universe would likely correct this imbalance in a violent and immediate way. Yet, against this seemingly insurmountable wall, physicists have dared to speculate. One fascinating, though highly theoretical, idea involves the ultimate fate of the universe. Some cosmological models suggest that if the universe eventually stops expanding and begins to contract under its own gravity, the arrow of time might reverse along with it. In this Big Crunch scenario, entropy could begin to decrease as the universe collapses back into a hot, dense state. In such a universe, time would effectively run backwards from our perspective. Beings there would remember what we consider the future and anticipate what we call the past. For them, traveling to their past would be traveling to our future, a mind-bending concept that turns everything on its head. However, current astronomical evidence strongly suggests our universe is not destined for a big crunch, but will continue expanding forever, making this an unlikely solution. A more practical, though still fantastically advanced, approach might be to manipulate entropy not on a universal scale, but on a local one. If a civilization could somehow create a bubble of space-time where the thermodynamic arrow of time pointed in the opposite direction, they could effectively isolate themselves from the increasing entropy of the wider universe. Inside this bubble, time could flow backwards relative to the outside, allowing for travel into the external world's past. Creating such a bubble would require technologies that can meticulously control the state of every single particle within it, effectively rewinding their entropy. The energy and computational power required for this is so astronomically vast that it borders on magic with our current understanding, but it establishes a theoretical loophole. It suggests that the arrow of time, while a powerful dictator on a cosmic scale, might be a local ordinance that could be overturned by a sufficiently advanced governing body of physics. This profound connection between time and entropy grounds the wild dream of time travel in the concrete science of thermodynamics. It moves the challenge from the abstract geometry of general relativity to the tangible, statistical behavior of matter and energy. It's no longer just about bending space. It's about fighting the universe's inherent tendency toward chaos and disorder. Any credible design for a time machine must therefore be, at its heart, a magnificent entropy reversal engine. This monumental hurdle naturally pushes our imagination toward the most extreme realms of physics, to substances and energies that seem to defy the very laws we are trying to circumvent. So if the ultimate time machine requires us to fight the universe's tendency toward disorder, what kind of power source could possibly fuel such an endeavor? This brings us to one of the most speculative yet scientifically grounded ideas in all of physics, the quest for negative energy and exotic matter. Imagine a substance that doesn't just have zero energy, but possesses negative energy density. This isn't merely the absence of gravity, it's a form of matter that would gravitationally repel everything around it. It sounds like pure magic, but incredibly, the laws of quantum mechanics don't forbid its existence. In fact, we've already observed tiny, fleeting glimpses of it in laboratory experiments. The most famous demonstration is the Casimir effect. If you take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, they will be gently pulled toward each other. Why? Because the empty space between the plates isn't really empty, it's a seething quantum foam teeming with virtual particles that constantly pop in and out of existence. However, the narrow gap between the plates restricts the kinds of quantum fluctuations that can occur there, while the space outside the plates remains wild and active. This creates a pressure difference, with more virtual particles pushing on the plates from the outside than from the inside. From a certain perspective, the region between the plates can be said to have a lower energy density than the surrounding vacuum, a kind of negative energy. It's an infinitesimally small effect, but it's real, measurable, and it proves that the quantum world allows for these bizarre energy states. The monumental challenge, of course, is scaling this phenomenon up from the microscopic realm of nanometers and virtual photons to something that could be used in an engineering project of cosmic proportions. To stabilize a traversable wormhole large enough for a spaceship, or to create a warp bubble that contracts space-time in front of a ship and expands it behind, we wouldn't need just a tiny amount of negative energy. We would need an amount equivalent to the mass energy of a star, or even an entire galaxy, converted into this exotic form. Furthermore, this exotic matter would need to be configured with incredibly specific and precise properties to prevent the wormhole or warp bubble from instantly collapsing. The sheer technological and energetic hurdle is so vast that it places this concept firmly in the realm of what physicist Michio Kaku calls a Type 3 civilization technology, something only a culture that has harnessed the power of an entire galaxy could even attempt. This hasn't stopped brilliant theorists from mapping out the blueprints. The most famous is undoubtedly the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. His solution to the faster-than-light problem was ingenious. Instead of trying to move a ship through space faster than light, which is forbidden, he suggested moving the space around the ship. Imagine standing on a moving walkway at an airport. You're moving relative to the floor, but you're just walking normally. The Alcubierre drive would be like creating a moving walkway of space-time itself. The ship would sit inside a flat region of space, a warp bubble, while the fabric of space-time in front of the bubble is massively compressed and the space-time behind it is expanded. In this way, the bubble and everything inside it could, in theory, be propelled to effective speeds beyond light speed without ever locally breaking the cosmic speed limit. The catch: the drive requires negative energy to create and sustain the warp bubble structure. The energy calculations for such a feat are truly humbling. Early estimates suggested the energy requirement was equivalent to converting the mass of Jupiter into pure energy. Later refinements have brought that number down significantly. Some theories even suggest it could be reduced to the mass of a spacecraft like Voyager 1. However, these more optimistic models come with their own set of daunting constraints and are still hotly debated. The fundamental problem remains: we have a mathematical recipe, but we are missing the most critical ingredient, and we have no idea how to farm it on an industrial scale. This leads to a fascinating and speculative leap. If such technology is permitted by the laws of physics but is impossibly far beyond our current capabilities, could it be that other, older civilizations in the galaxy have already mastered it? The idea that advanced extraterrestrial beings might not just be crossing space but also navigating time is a staple of science fiction and UFO lore. Perhaps some of the unexplained aerial phenomena witnessed throughout history are not visitors from another star system, but time travelers from our own future or from a parallel reality, using their command over exotic physics to observe timelines without interfering. Maybe they follow a strict temporal prime directive, understanding the profound dangers of paradoxes and causality violations. This line of thinking expands the search for extraterrestrial intelligence into a new dimension, literally. We might not just be listening for signals from across space, but also for echoes from across time, evidence of a technology that has tamed the most fundamental forces of the cosmos to turn the universe into a navigable four-dimensional landscape. This idea takes our speculation about time travel and launches it into the cosmos on an epic scale. If the laws of physics permit journeying through time, then it's not just a potential future for humanity. It could be a common technology for civilizations that have been exploring the stars for millions or even billions of years longer than we have. Imagine a galactic community where the most advanced species don't just navigate the three dimensions of space, but all four dimensions of space-time as easily as we sail across an ocean. From their perspective, visiting ancient Earth to observe the dinosaurs or witnessing the construction of the pyramids might be as simple as we consider visiting a national park or a historical monument. They wouldn't be coming from a distant star, they could be coming from our own future or from a parallel timeline entirely, using technologies that render our current understanding of physics utterly primitive. This concept provides a fascinating new lens through which to view some of history's most enduring mysteries. How do we explain the astonishing precision of ancient megalithic structures like Puma Punku or the Great Pyramid, feats of engineering that we would struggle to replicate even with modern machinery? What about sudden bursts of knowledge or artistic revolution that seem to appear out of nowhere in the archaeological record? While mainstream science offers its own explanations, the theory of extraterrestrial time travel offers a tantalizing, albeit entirely speculative, alternative, that these could be signs of observation or even subtle guidance from visitors not just from other worlds but from other times. They might be cultural anthropologists on a grand scale, studying the rise and fall of civilizations across eons without ever revealing their presence in a blatant way. This theory also elegantly addresses one of the most persistent questions in the search for extraterrestrial intelligence, known as the Fermi paradox. If the universe is so vast and old, where is everybody? If time travel is part of the answer, then they might not just be out there in space, they could be all around us in time, hidden in plain sight. Their technology would likely be so advanced that remaining undetectable would be trivial. They could be following a strict protocol of non-interference, a temporal prime directive, to avoid contaminating the timeline of a developing species like ours. The last thing a truly advanced civilization would want is to create a paradox or alter the natural course of history that led to their own existence. Their mission might be one of pure observation, ensuring they leave no more trace than a ghost passing through a room. This shifts the entire paradigm of UFO sightings and alleged encounters. Rather than simply being spacecraft from a nearby star system, some of these unexplained phenomena could be time ships, vehicles designed for temporal navigation as much as spatial travel. The bizarre characteristics often reported, like sudden appearance and disappearance, silent operation, and ability to defy inertia, could be side effects of a propulsion system that manipulates spacetime itself, not just for flight but for chronological leaps. A craft might not just zip away into the sky, it could fade from view as it moves a few minutes into the future or past relative to our perception. While this remains firmly in the realm of speculation without a shred of concrete evidence, it's a powerful and inspiring synthesis of ideas. It merges the dream of finding other intelligent life with the dream of mastering time, suggesting that the two might be inextricably linked. It expands the canvas of possibility from our lonely little planet to the entire history of the universe, implying that the greatest adventures might not be about going to other planets, but about witnessing other eras. And it gives us a humbling perspective. We may not be the pinnacle of creation, but simply a fascinating chapter in a cosmic story being quietly studied by historians from a future we can scarcely imagine. But what if the ultimate time machine isn't something you build or find, but is the entire universe itself? We've explored cosmic strings and wormholes as potential pathways through time, but this next idea is perhaps the most profound of all. Some of the solutions to Einstein's own equations for general relativity suggest a staggering possibility that the entirety of spacetime might be curved back onto itself in a colossal loop known as a closed time-like curve. In this model, if you were to get in a spaceship and travel in a perfectly straight line for an unimaginably long time, you wouldn't just eventually return to your starting point in space. You would return to the very moment you left in time. The cosmos wouldn't be an infinite, ever-expanding stage. It would be a finite, four-dimensional hypersphere where the future literally wraps around to meet the past. This isn't just a journey through time. It's an entire universe where time travel is a fundamental property of existence. History wouldn't be a linear march forward, but a continuous, repeating cycle. Every event from the birth of the first star to the reading of this sentence would be destined to play out again and again forever. Your life, with all its joys and sorrows, its triumphs and regrets, would be on an infinite replay loop. This concept dovetails beautifully with ancient cyclic models of the cosmos found in various philosophies and religions, like the Hindu concept of Kalpa or the Greek idea of the Great Year, where creation and destruction occur in endless succession. Even some modern cosmological theories, like the conformal cyclic cosmology proposed by Roger Penrose, suggest that the end of one universe could be the Big Bang of the next, creating an eternal cycle of rebirth. The implications for our understanding of reality are nothing short of earth-shattering. If the universe is a closed time-like curve, then the distinction between cause and effect completely dissolves. The future would be just as real and fixed as the past, and your actions today would be both the cause and the effect of events that occurred billions of years ago. It creates a kind of cosmic, self-consistent loop on the grandest possible scale, where everything is simultaneously the origin and the destination. This would be the ultimate expression of the Novikov self-consistency principle, applied not to a single time traveler, but to every single particle and event in existence. Paradoxes would be impossible by the universe's very architecture. This naturally forces us to confront those deepest questions about identity and free will with terrifying new intensity. If the universe is a fixed, immutable loop, then we are all characters in a story that has been written, read, and rewritten an infinite number of times. Every choice you believe you are making freely, what to eat for breakfast, who to fall in love with, which path to take, would be an illusion. You are simply acting out a part that has been performed countless times before and will be performed countless times again. The you that exists now is just one iteration of an eternal pattern. This can feel deeply nihilistic, robbing life of any genuine novelty or meaning. Yet, one could also find a strange comfort in this cosmic symmetry, a sense that we are all integral, eternal threads in an unimaginably vast and beautiful tapestry that is the universe itself. However, it is crucial to note that while this is a mathematically valid solution to Einstein's field equations, it is not supported by our current astronomical observations. All the evidence we have, from the geometry of the universe to the patterns in the cosmic microwave background, strongly suggests that our universe is flat and infinite, not closed and finite. The closed, time-like curve universe remains a fascinating thought experiment, a haunting what if that pushes our understanding of physics and philosophy to their absolute limits. It serves as a powerful reminder that the nature of time itself is the greatest mystery we face, and that the answers may be far stranger and more wonderful than we have yet dared to dream. Now let's venture into one of the most speculative and wonderfully strange ideas on our list, a concept that suggests time travel might not require a machine or a cosmic string, but could instead happen purely by chance as a random gift from the unpredictable quantum world. This is the theory of time travel via quantum tunneling, and it asks us to consider whether the universe's smallest, weirdest rules could ever apply to something as large and complex as a human being. To understand this, we first need to grasp the bizarre phenomenon of quantum tunneling. In the everyday world, if you roll a ball toward a hill, it will only make it to the other side if it has enough energy to get over the top. If it doesn't, it rolls back. That's classical physics, but in the quantum realm, particles like electrons don't play by those rules. An electron faced with an energy barrier it shouldn't be able to cross doesn't always bounce back. There's a small but real probability that it will simply appear on the other side, as if it somehow tunneled through the hill instead of going over it. It hasn't broken any laws, it's simply leveraged its inherent wave like nature and the fuzzy uncertainties of quantum mechanics to bypass a classical limitation. This isn't just a theory, it's a well-documented effect that is crucial to the operation of modern electronics and even plays a role in nuclear fusion within stars. The radical leap in this theory is to ask, if a single particle can tunnel through a barrier in space, could a macroscopic object, like a molecule, a dust speck, or even a person, tunnel through a barrier in time? Instead of facing a physical hill, imagine facing a temporal barrier, a point in time you cannot reach through normal, classical means. Proponents of this highly speculative idea suggest that, given the right conditions and an almost infinitely small probability, an object might undergo a quantum fluctuation that effectively teleports it to another point in time. It wouldn't travel along a continuous path through the years. It would simply cease to exist in one moment and pop into existence in another, a statistical miracle defying all conventional logic. This idea gains a fascinating, though purely theoretical, foothold when we consider the scale of the universe. In an infinite cosmos with infinite time and infinite particles, even events with an infinitesimally small probability are not just possible, they are inevitable. Given enough time and enough space, anything that can happen will happen somewhere. So, in a universe that is truly infinite, perhaps these bizarre temporal tunneling events occur spontaneously all the time. A single atom might randomly tunnel back a nanosecond, or a specific arrangement of particles might jump a millennium. Of course, the probability of an entire, coherent human being, a vastly complex arrangement of countless atoms all tunneling in perfect synchrony to the same point in the past, is so unimaginably small that it effectively rounds down to zero. The chances are so remote that it makes winning every lottery in the galaxy simultaneously look like a sure bet by comparison. This is why the theory remains firmly in the realm of philosophical curiosity rather than practical physics. It's a thought experiment that highlights the vast, often unbridgeable gap between the quantum weirdness of the microscopic world and the stable, predictable reality we experience at our scale. While a single particle can be in two places at once or tunnel through walls, these effects are averaged out in larger objects. The sheer number of particles in a human body, all interacting and decohering with each other and their environment, makes any coordinated quantum event like temporal tunneling a virtual impossibility. It's a captivating what-if that fuels the imagination, but it doesn't provide a blueprint for a time machine. Yet the idea holds a certain poetic beauty. It suggests that time travel might not always be a matter of engineering and control, but could instead be a rare, spontaneous, and utterly random act of the cosmos. It turns time travel into a natural phenomenon, like a cosmic lightning strike, unpredictable and uncontrollable. This shifts the narrative from one of human ambition to one of cosmic chance, a reminder that the universe might hold wonders that defy not only our technology, but also our very understanding of probability and scale. But with the profound power to navigate time comes an even more profound responsibility, forcing us to confront questions that lie at the very heart of morality and human nature. If we ever unlock the secrets of temporal travel, the first and most critical manual we'll need to write won't be about physics or engineering. It will be a code of ethics, a guide for wielding a power that could unravel reality itself. The most famous fictional example is Star Trek's Prime Directive, a strict rule of non-interference designed to protect developing civilizations from the corrupting influence of advanced technology and knowledge. Apply that to time travel and the directive becomes even more absolute. Do not interact, do not change, do not even be seen. The potential for catastrophic, unintended consequences is simply too high. Consider the terrifying ripple effects of even a seemingly minor change. A time traveler stepping on a single insect in the Jurassic period could theoretically set off a chain of events that alters entire ecosystems, potentially preventing the evolution of key species millions of years later. A well-intentioned trip to prevent a historical tragedy, like the assassination of a beloved leader, might inadvertently create a far worse timeline, one where their continued presence leads to a devastating war or the suppression of a crucial social movement. The past is an impossibly complex and delicate web of cause and effect. Pulling on a single thread could make the entire tapestry unravel in ways we could never predict. This isn't just about avoiding a personal paradox like erasing your own birth. It's about the ethical duty to preserve the integrity of history itself for the sake of every living being that has ever existed. This leads to a deeply unsettling philosophical dilemma. Does the past have rights? Do the people living in what we consider history possess an inherent right to their own timeline, free from the meddling of visitors from the future? If we observe a horrific historical event, like a natural disaster or a terrible battle, do we have a moral obligation to intervene and save lives, even if it risks altering the future? Or does our knowledge of the eventual outcome, that humanity survived and progressed beyond that point, oblige us to stand by and allow the suffering to happen? This is a chilling form of utilitarianism on a cosmic scale, where the traveler must weigh immediate suffering against potential future good, playing God with the lives of billions. Beyond the grand, world-altering decisions, there are more intimate ethical concerns. What about the temptation of historical tourism? Would it be morally acceptable to simply visit the past as a spectator, to witness the construction of the Great Pyramid or hear Abraham Lincoln deliver the Gettysburg Address? Even without direct interference, the mere presence of an observer from the future could be disruptive. A dropped piece of future technology, a modern-day pathogen to which ancient people have no immunity, or even just the psychological impact of an encounter could irrevocably contaminate the timeline. The desire for knowledge and experience would have to be balanced against a strict principle of preservation, treating the past as the ultimate protected wilderness area. And who would get to decide the rules? The governance of time travel presents a monumental political and legal challenge. Would a single nation or corporation control the technology, imposing its own ethical framework on all of history? Or would we need a global, or even intertemporal, regulatory body to establish and enforce a universal temporal accord? The potential for abuse is staggering. Imagine a totalitarian regime using time travel to erase dissent from history, or to ensure its own rise to power. The very concept of justice would need to be redefined for a reality where evidence could be planted or removed from the past, and alibis could be manufactured across centuries. These aren't abstract thought experiments. They are essential considerations that highlight how time travel wouldn't just change our understanding of physics, but would fundamentally challenge our societal structures, our laws, and our very notions of right and wrong. It reminds us that the greatest challenge of time travel may not be building the machine, but developing the wisdom to use it without destroying everything we hold dear. But what if we dared to move beyond pure theory and actually tried to draft the blueprints for a time machine? While we may lack the materials and energy to build one, the human mind has already sketched out some astonishingly detailed designs, transforming wild science fiction into legitimate scientific speculation. These aren't just fanciful drawings, they are mathematical models grounded in the hard equations of general relativity, offering us a glimpse into what a future of temporal engineering might one day require. The most famous of these designs is the Tipler cylinder, proposed by physicist Frank Tipler in 1974. Imagine a cylinder made of an impossibly dense material, perhaps the stuff of neutron stars, stretching for 100 kilometers or more and spinning at a breathtaking pace, billions of rotations per minute. This isn't just a spinning top, it's an object so massive and moving so fast that it doesn't just warp space-time, it literally drags it along, twisting the fabric of the universe around it like honey stirred by a spoon. The magic happens in the space around this gargantuan, spinning cylinder. The frame-dragging effect would be so intense that it could create a path through space-time that loops back on itself, a closed time-like curve. To travel in time, a spacecraft wouldn't even need to enter the cylinder. It would simply need to navigate a precise figure-8 orbit around this cosmic whirligig. Complete a few loops on this twisted spacetime track, and you could find yourself returning to your starting point not just in space, but in time. It's a compelling vision, but the practical hurdles are, to put it mildly, astronomical. First, we would need a material with the density of a neutron star, but the structural integrity to hold its shape while spinning at relativistic speeds without flying apart. We have no known material that could withstand such forces. It would require a substance far beyond any alloy or composite we can currently conceive of. Second, the energy required to spin such a colossal object to those velocities is beyond our comprehension, likely requiring the total energy output of a star. Another design we've touched on revisits the concept of cosmic strings, rather than hoping to find two strings moving perfectly past each other as J. Richard Gott proposed a more advanced civilization might attempt to manipulate a single string. The idea would be to take this infinitely dense cosmic filament and bend it into a specific loop or configuration. The gravitational field of this loop could then create a closed time-like curve in its immediate vicinity. While this avoids the need for the precise high-speed collision of two strings, it introduces the even more daunting challenge of how one would possibly manipulate an object with the mass of a mountain range per inch. The technology required would be nothing short of godlike, involving forces and energies that dwarf anything we see in our universe today. What unites all these theoretical blueprints is their reliance on extremes, extreme densities, extreme speeds, and extreme energies. They are less like practical engineering plans and more like thought experiments that test the boundaries of Einstein's theory, proving that time travel is not forbidden by the laws of physics as we currently understand them. They show us that the barrier is not a fundamental no from the universe, but a monumental not yet from our technology. Building a Tipler cylinder or manipulating a cosmic string is so far beyond our current capabilities that it might as well be magic, but it establishes a crucial principle. The universe's rulebook might contain the instructions for a time machine. We just lack the tools, the materials, and the power to follow them. For now, these designs remain beautiful, tantalizing puzzles, a bridge between the abstract mathematics of relativity and the enduring human dream of touching the past or leaping into the future. They challenge us to keep pushing the boundaries of what we believe is possible, inspiring the next generation of physicists and engineers to wonder if, one day, the impossible might just become a matter of solving an incredibly difficult engineering problem. But perhaps the most tangible and experimentally verified path to time travel doesn't require cosmic strings or exotic matter, but simply demands that we push the boundaries of speed itself. This brings us to a cornerstone of modern physics, Einstein's special theory of relativity, which reveals an astonishing and intimate connection between motion and time. The theory makes a clear, testable prediction. The faster you move through space, the slower you move through time relative to someone who is stationary. This effect, known as time dilation, is not a vague theory. It's a concrete reality that we must account for in our most advanced technologies. The mathematics of relativity are both elegant and profound. As an object's velocity increases, approaching the ultimate cosmic speed limit, the speed of light, the passage of time for that object, as measured by an outside observer, slows down dramatically. Imagine embarking on a journey aboard a spacecraft capable of traveling at 90% the speed of light. For you on the ship, the trip might feel like a few years. But upon your return to Earth, you would discover that decades had passed for everyone you left behind. You would have effectively traveled years into Earth's future. At the speed of light itself, the equations suggest time would come to a complete standstill. For a photon of light emitted from a distant star at the dawn of time, its entire journey across the universe is instantaneous from its own perspective. it does not experience the billions of years that pass for the rest of the cosmos. It is born and arrives in the same moment, a timeless traveler. This naturally leads to a tantalizing, though speculative, question. What happens if something could somehow exceed the speed of light? The theory suggests that if such a thing were possible, its clock would not just slow down but would actually run backwards, effectively sending it into the past. This is the realm of tachyons, a hypothetical class of particles that are born traveling faster than light. By their very nature, if they could interact with us, they might appear to be moving backwards in time. They have become a staple of theoretical physics and science fiction for this very reason, representing a potential mechanism for sending information or even matter into the past. However, despite extensive searches, tachyons have never been detected. Most physicists believe they do not exist, as their presence would wreak havoc on our understanding of causality and lead to the very paradoxes we've been exploring. The cosmic speed limit of light appears to be a fundamental rule that matter and energy cannot break. Yet, the relativistic time dilation we can achieve is a form of time travel that we have already proven and utilized. The global positioning system is a perfect example. The satellites in the GPS network are moving at significant speeds relative to the Earth's surface. According to special relativity, the clocks on these satellites should run slightly slower than clocks on the ground. If this effect weren't meticulously calculated and corrected for, the entire system would become inaccurate within minutes, and your smartphone's navigation would lead you astray. Even more personally, astronauts on the International Space Station, due to their high orbital velocity, experience time ever so slightly slower than we do on Earth. After a long mission, they are technically a fraction of a second younger than they would have been if they had stayed home. It's a minuscule effect, but it's real, measurable, and it proves that the engine for traveling into the future is written into the fundamental laws of our universe. The challenge, of course, is scaling this effect up from fractions of a second to meaningful journeys into the deep future. To experience a significant leap, a spacecraft would need to sustain velocities incredibly close to the speed of light for a substantial period. The energy requirements for such a feat are currently unimaginable, likely requiring the total energy output of our entire civilization harnessed for years. Furthermore, the engineering obstacles are immense, from shielding the ship from interstellar dust, which would impact with the force of a nuclear bomb at those speeds, to designing a propulsion system we can't yet conceive of. Projects like Breakthrough Starshot, which aims to send tiny, laser-propelled probes to a nearby star at a significant fraction of light speed, offer a glimpse into this potential future. If successful, those tiny probes would not only travel through space, they would also be traveling through time, arriving at their destination in their own time frame while centuries may have passed back on Earth. This is the most realistic form of time travel currently within our theoretical grasp, a one-way ticket to the future, powered by nothing more than the relentless and beautiful logic of motion itself. After this incredible journey through 19 of the most mind-expanding theories on time travel, from the quantum realm to the cosmic scale, we arrive at a final, humbling, and perhaps most important idea of all. We must now turn the lens back on the very concept itself and ask the ultimate meta question: could the dream of time travel be logically impossible from the start? Not because of our technological limitations, but because the universe's own fundamental rules might contain built-in safeguards that make it an unattainable fantasy. This is the profound and sobering argument put forward by some of the greatest scientific minds, a suggestion that the cosmos might be hardwired to prevent paradoxes from ever occurring, protecting the very fabric of causality. The most famous proponent of this view was the legendary Stephen Hawking. He humorously, yet pointedly, challenged the idea with his chronology protection conjecture. Hawking essentially argued that if time travel to the past were possible, we should be overrun with tourists from the future. Where are they? The fact that we haven't been inundated with visitors, he suggested, is the strongest evidence that it simply cannot happen. He proposed that the laws of physics, particularly at the quantum level, would always conspire to prevent the formation of a closed time-like curve, a path through spacetime that loops back on itself. The universe might employ any number of mechanisms to enforce this protection. A wormhole might collapse at the exact moment it becomes a time machine. A quantum fluctuation might disrupt a spinning Tipler cylinder, or the energy required might always become infinite at the crucial moment. In this view, reality has a kind of immune system designed to prevent temporal infections that would cause a fever of paradoxes. This idea encourages a deep and necessary humility. It reminds us that while the mathematics of general relativity might allow for solutions that permit time travel, the universe is not governed by geometry alone. We must also contend with quantum mechanics, thermodynamics, and perhaps laws of physics we haven't even discovered yet. The pursuit of time travel forces these different domains of physics into a head-on collision, and the chronology protection conjecture is the compelling argument that when they crash together, time travel is always the loser. It suggests that the universe values consistency and causality above all else, and it is structured to preserve them at any cost. Yet, even if this final theory proves true and time travel remains forever locked away in the realm of thought experiments, its value is undiminished. The incredible effort to understand it has been one of the most powerful engines for scientific progress in human history. The struggle to resolve the grandfather paradox pushes the boundaries of logic and philosophy. The mathematics behind wormholes and warp drives deepens our mastery of general relativity. The bizarre predictions of quantum mechanics, with their retrocausal hints, force us to rethink the very nature of reality. By chasing this beautiful, elusive dream, we haven't been wasting our time. We've been uncovering the deepest secrets of the universe. The question of time travel is a brilliant torch that illuminates dark corners of physics we might never have otherwise explored. And in that light, we have found wonders far stranger and more magnificent than any simple time machine could ever be. And so our journey through the corridors of time comes to a close, but the echoes of these incredible ideas will linger long after this video ends. We've ventured from the intimate, terrifying logic of the grandfather paradox to the cosmic scale engineering of hypothetical strings left over from the universe's fiery birth. We've wrestled with the self-creating loops of the Bootstrap effect, danced through the infinite branches of the many worlds interpretation, and felt the gravitational drag of a black hole's relentless pull on the fabric of spacetime itself. Each theory, from the quantum to the cosmological, has offered us a unique lens, a different set of keys to try in the locked door of time, challenging everything we thought we knew about cause and effect, reality, and our own place within this vast, mysterious cosmos. It is crucial to remember that while we may not be building working time machines in our garages anytime soon, the relentless pursuit of these concepts is far from a futile exercise. This is where pure, unadulterated curiosity becomes the engine of human progress. The struggle to resolve a paradox like the grandfather effect pushes the boundaries of logic and computer science. The mathematics required to describe a stable wormhole deepens our mastery of geometry and gravitational physics. The bizarre, counterintuitive results of quantum entanglement experiments force us to invent entirely new fields of information theory. The dream of time travel, however distant, forces these different domains of science into a brilliant, productive collision. In trying to answer one of our biggest questions, we have uncovered a universe of deeper, more fundamental truths. We haven't been wasting our time chasing a fantasy. We've been using a magnificent dream as a guide to map the very real and astonishing terrain of reality. This is the true legacy of this intellectual adventure. It is a powerful testament to the words of Carl Sagan, who reminded us that somewhere, something incredible is waiting to be known. The greatest discoveries often begin not with a practical goal, but with a wondering question whispered in the dark. What if the questions we've explored today are not just for physicists in ivory towers? They are for anyone who has ever looked up at the night sky and felt a sense of awe, for anyone who has ever wondered about the road not taken or dreamed of witnessing history firsthand. This relentless curiosity, this refusal to accept the surface appearance of things, is what propels us forward. It is the very essence of exploration, whether we are navigating the oceans of space or the deeper oceans of theoretical possibility. Your engagement with these mysteries doesn't have to end here. The conversation is just beginning. We want to hear which of these 20 theories bent your mind the most. Was it the philosophical punch of the Novikov self-consistency principle, or the cosmic grandeur of the block universe? Do you think time travel is a future inevitability or a logical impossibility? Share your thoughts, your own favorite time travel stories, and your biggest questions down in the comments below. Let's get a fantastic discussion going. If this journey through the cosmos sparked your imagination, please show your support by liking this video and subscribing to the channel for more deep dives into the universe's greatest mysteries. There is so much more to explore, from the nature of dark matter to the search for extraterrestrial intelligence. Until our next adventure together, never stop questioning, never stop wondering, and as always,